Good morning and welcome everyone to the ones who are here and the ones who are watching us in our YouTube channel. It's a pleasure to have here Carlos Hernández. He was invited to come to give a seminar in March 2020 and it was not possible. So we are very happy that you are here today. Before starting the seminar, I want to say a few words about his career. He is a Harmonic Half Fellow at the University of Salamanca, where he leads the European Research Council starting grad project Attostructura. And previously, he was a Marie Curie Fellow at Gila, University of Colorado, and he is renowned for his theoretical contribution to attosecond science and ultrafast nonlinear optics. His theoretical work on strong field laser physics has been strongly connected to experimental laser and X-ray science, and he has participated in the development of ultrafast structured light with notable achievements that paved the way for the experimental demonstration of circularly polarized high harmonic attosecond pulses, ultrafast vector beams, Selftorque beams, and extreme ultraviolet soft X-ray harmonic pulses with controlled orbital angular momentum. These achievements have enabled the practical implementation of another class of laser-driven coherent X-ray sources structured in their spectral, temporal, and angular momentum properties. He has been recipient of the European Physical Society Quantum Electronics and Optics Division Fresnel Prize in 2019 for fundamental aspects, the Physics Prize of the Spanish Royal Society of Physics 2019 as Young Researcher in Theoretical Physics, and the UPAP Young Scientist Prize in Atomic, Molecular, and Optical Physics 2021. He is president of the Quantum Optics and Nonlinear Optics groups at Optical and at the Spanish Royal Society of Physics. Too many things. Congratulations. So now you can start with the seminar, and thank you very much.
Thank you very much, Esther. Well, thank you all those who are here and those who are online. It's a pleasure for me to be here to come to give a talk. As Esther said, it was a pity that I couldn't come on March 2020, and I'm really happy, and I think we all are happy that we can retake these seminars and we can retake the normal activity. And well, now it's my responsibility so you can enjoy it, and at least you can learn something, a little bit of the research we are doing. So thank you a lot for inviting me to come here. And well, what I'm going to talk about today is more or less like a review of the things we've been doing during the last years. Okay, it's something relating to what's the title of my talk, about the structuring laser light and structuring ultrafast laser light using nonlinear physics, using nonlinear optics. Okay, so I'm going to be talking about the structuring light. Okay, but I'm going to be talking about the structuring ultrafast laser light. What does this mean? Is that we are going to shape laser light at ultrafast timescales. Okay, as some journalists said, okay, we are going to do like donuts or croissant shaped light, okay, with the sources we are going to generate. But it's important here to remark the temporal character of this structure. Okay, I'm going to be talking about ultrafast laser light. And for those who are not familiar with ultrafast optics and ultrafast lasers, let me review what are the different timescales in which we are involved when talking about this kind of pulses. So if we review more or less the timeless, we can establish like the second as the reference from our timescale, yeah, like the heart beating. It's like a reference. If we go to higher timescales, we have 10 to the 3 seconds, like an hour, more or less the duration of this talk. And this is like well known for us. Okay, what is happening for higher timescales? Of course, we can go for days, years, etc., and we will arrive to the highest timescale that we know, the largest one, which is the age of the universe, which is estimated to be like 10 to the 18 seconds. Okay, what happens if we go now to the other way around? We go to lower time, the fastest process. Okay, we have milliseconds, which is mostly related something related we can imagine like the flapping of a hummingbird or the time scales of Formula One. If we go down, we have microseconds, okay, which are the time scales of the chemistry of life. We can go down nanoseconds, 10 to the -9, which is more or less the speed of our processors, yeah, gigahertz. The speed at which we can control nowadays the movement of electrons. If we go down, we have picoseconds, which is the time scale, the typical time scale of chemical reactions. 10 to the -12, 10 to the -15, this is femtoseconds. Okay, here we can analyze, for example, the electronic transmigration of the molecules. And then in 10 to the -18, we have attoseconds, okay, which is the time scales in which nowadays we are able to generate extremely short laser pulses. What happens at these time scales? This is the standard time scale of, for example, electrons moving around atoms. Okay, so once we have more or less these time scales, our objective here, our goal now is to be able, of course, to observe different processes that happen at different time scales. I'll be talking about processes at the shortest time scales. So what are the tools that we have to observe those time scales? Well, the main idea here we have to keep in mind is that we need a camera that is fast enough to be able to interact to the process that happens at each time scale. For example, we are making a picture of someone that is running, and it's running too fast compared to the capability of our camera. Of course, the image will be blurry. We cannot observe that process. Okay, so that's more or less the idea that we have to keep in mind here. Okay, so what are the tools we have nowadays? We have mechanic tools, which is the standard cameras that we are used to. Okay, they can reach time scales. The shutter of this mechanical or electronic shutter of the standard cameras are in the 10 to the -4, 10 to the -5 seconds. Okay, if we want to go deeper or lower, then we have electronics. Okay, as I say, the movement of electrons, the gigahertz processors that we are using nowadays, they are in this time scales of 10 to the -9 the nanoseconds. But if we would like to observe processes that happen at even shorter time scales, then we have to recall we need optics. Okay, optics is the only way to reach those time scales. Optics, and in particular lasers, and more particular, not heavy laser, but pulse lasers. Okay, and we will be talking about very small, very short pulses of light. Okay, with these pulse lasers that can reach these time scales of pico, femto, or even attoseconds. And we have to keep in mind that these lasers, we can use them as a ruler. Okay, because depending on the separation of different pulses and the time duration of different pulses, we can use them as a ruler for observe the processes that take place at those times. So what do we need to be able to build these laser pulses at these so short time scales? We need basically two things. Okay, we need first, we have to take into account the optical size. Okay, we have the wavelength of our laser light, okay? And of course, we cannot have a pulse which is shorter than one cycle, at one period, because then there is no definition of a pulse. Yeah, so the minimum pulse duration, of course, it will be always the period of the laser light we are using. For example, if we use 800 nanometer laser light, okay, the period is 2.67 femtoseconds. Of course, that's the shortest we can achieve. But we have another thing. Yeah, we have the limitation of the uncertainty principle given by the spectral boundary. Okay, the pulse duration is limited by the spectral bandwidth of our pulse. Okay, so the development during the last years, development in the laser technology has enabled nowadays to have intense femtosecond laser sources. Okay, very routinely based on titanium sapphire technology, and also it was recognized the Nobel Prize in 2018 in physics for the technique of shear pulse amplification that enabled the generation of femtosecond laser pulses with quite intense. So if with these pulses, as I said, or I don't know if I said, but these pulses are centered at 800 nanometers because that's the wavelength of emission of titanium sapphire, which is the technology, an active medium of these lasers. And with titanium sapphire, 800 nanometers, of course, the shortest pulse that we can achieve is 2.67 femtoseconds. And nowadays, there's been already measurements, here I mentioned 2 different works, of femtosecond laser pulses with almost 1 cycle in duration. Okay, so this is more or less the minimum pulse duration we can achieve with this technology with half of intense laser pulses of titanium sapphire. So what do we need if we would like to go to shorter pulses, if we would like to go to the attosecond timescale? So you can understand, we need first, we need higher frequencies, yeah, to be able to to reduce the duration of the period of our laser pulse. So, for example, if we go to the extreme ultraviolet, within the 3 nanometers, we can have a period already of 10 attoseconds. Okay, this is the first thing we need, but we need, as I said, due to the uncertainty principle, we need a lot of frequencies. Okay, we not only we need frequency in the extreme ultraviolet or even in the soft X-rays, that will be even shorter pulses, but we need a lot of frequencies. So if we go to the electromagnetic spectrum, okay, more or less here is where we are for femtosecond pulses. We need laser emission in this regime, more or less. If we would like to go to, if we would like to achieve attosecond pulses, we will need something like this. Yeah, not only to go to higher frequencies in the, let's say, extreme ultraviolet or even in the soft X-rays, but also we need huge band, really high band. Okay, how can we achieve this with laser light? You may notice that it's very difficult to have an active medium of a laser that goes to these higher frequencies. Okay, there is no an active medium that can generate radiation, coherent radiation with these higher frequencies. So the approach that we followed and the community has followed is to use nonlinear optics. Okay, let me remind you the basics of nonlinear optics. But we know, for example, if we have an intense laser of 800 nanometers, titanium sapphire, and we shine a material, some material, not every material, but some material. So of course, we can treat the perturbation of the electrons in the material perturbatively, okay? And we know that if we calculate the polarization, we have the linear polarization, which is the response of the medium, but we have also another term, which is the nonlinear polarization, okay? That we have there. And as a consequence, we have the emission of, in this case, second harmonic, okay? So this is well known for probably from your courses of optics. Okay, but if we generate, for example, the second harmonic of 800 nanometers, it will be 400 nanometers, will be here. We need to go deeper into the higher frequency, higher regime of our frequency regime of our spectrum. We could go not only to second harmonic, but also to third harmonic, fourth harmonic. So, okay. But the problem is that, as I said, this is a perturbative regime. It means that the intensity of each harmonic is decreasing. Okay. And of course, if we would like to go to this region over here, the efficiency will be really, really low. Yeah, that's a problem that we have to solve. Fortunately, we can solve it. And we would like to have something like this. Yeah, we would like to have different harmonics, but with several of them with similar intensity. And this happens through the process of high-order harmonic generation. The basics are quite simple to understand. In perturbative harmonic generation, which is second, third harmonic, we are perturbating the electron. Yeah. In high-order harmonic generation, the laser intensity is higher, so we are disturbing the electron very, very much. Actually, we are ejecting the electron, we are ionizing the electron from the parent atom. Okay. I will tell you what are the physics that leads us to make this higher harmonic generation and to have this efficient generation of harmonics deeper into the high frequency regime, which is what we would like. Actually, this technique is quite versatile because, for example, if we derive harmonics not with 800 nanometers, but with 4 microns laser light, we can generate even a higher plateau going deeper into the surface. Okay. So, what's the basis of high harmonic generation? In high harmonic generation, basically, we have a pulse laser, 800 nanometers, titanium sapphire, which is focused into the gas jet. Okay. And Let us go into the gas jet. The gas jet is composed of many atoms, okay, typically argon or helium, neon, noble gases. And in each one of these atoms, when the infrared laser light, intense laser light arrives, the nonlinear interaction between the laser and every atom in the gas jet leads to the generation of higher frequency harmonics. If we go to one of these atoms, what happens is when the amplitude of the laser light is high enough, an electron wave packet can be ionized from the parent ion. Then this electron wave packet is accelerated by the laser light, but then it changes its sign in the direction due to the oscillatory behavior of the laser light, so it recombines back to the parent atom. So all the kinetic energy acquired from the laser light is emitted in terms of higher frequency radiation when recombining with the parent atom. And this happens every half cycle of our laser pulse. So at the end, we end up with a train of higher frequency pulses, okay, that are emitted due to this process of high order harmonic generation. So this is more or less the summary of this process: the infrared laser light, the gas jet, the pulses emitted, this what we call the three-step model: ionization, acceleration of the electron, and recombination. And we end up, how is this radiation emitted? So this radiation is emitted in the form of high order harmonics. Why there are harmonics that are being emitted? You can think very easily in translating from the time domain to the spectral domain. In the time domain, I think I have shown you why we have a train of pulses that are being emitted every half cycle. If we perform the Fourier transform of such emission, we end up that only odd order harmonics are allowed. Okay, this is one of the reasons why we have this emission of odd order harmonics: 1, 3, 5, 7, 9, etc. So what we can do now is, okay, we have now what we wanted. We have coherent emission that is going deep, it goes farther into the higher frequency regime. So if we select the higher order harmonics, something like this, we filter out the lower order harmonics and we select the higher order harmonics and we perform the Fourier transform, we obtain the emission of attosecond pulses, okay, pulses in the attosecond time. So this is the way in which nowadays we can generate the shortest light pulses what we now have now. We can understand also this process from the photon picture, and this will help us later when I'm going to talk about the structural light. This will help us to understand the scaling laws that we have there. We can think that in each one of these atoms, we are absorbing, for example, to generate the 15th harmonic, we are absorbing 15 infrared photons, and at the end, they are emitted in terms of 1/4, yeah, of the 15th order, higher frequency. Okay, so nowadays, we can reach the attosecond timescale thanks to harmonic generation. These are more or less the records. The shortest pulse that has been generated and measured is 43 attoseconds here, and also the broadest bandwidth of emission that has been generated is this one going to the soft X-rays. Of course, the problem here is if all this emission that goes from the mid-infrared into the soft X-rays is a huge bandwidth. If all this emission is emitted in phase, we would be able to have here like 2 attoseconds, something like this. The problem is that not all the harmonics are in phase. They have a chirp. Okay, the phase is regular. They have a chirp, but the chirp for this emission is huge. Actually, here this is a collaboration. We were working with the University of Colorado, and here we predicted that actually these pulses have a pulse duration of 2 femtoseconds due to the huge chirp that they have. But if we were able to compensate that chirp, that phase of subsequent harmonics, we would be able to decrease the pulse duration of this emission. Okay, so what can we do with attosecond pulses? Well, let me give you some brief ideas of what is being done nowadays. We can study charge migration inside molecules. Okay, so very nice experiments that are being done lately, and there are more updated references on this. We can also study ultrafast magnetism, the organization of magnetic domains in such timescales. I will talk about this later on. And these harmonic pulses are also used for imaging applications. These are more or less the most standard ones, but there are more of them that I can talk afterwards if you want. Okay, so more or less I've told you how can we generate these ultra-fast laser pulses, yeah? Pulses up to the attosecond timescale. But the title of my talk was about the structure like pulses. So what we've been working recently is like in adding new gadgets to our camera. Yeah, we have the timescale, which is absolutely required to be able to access these processes that happens in these timescales. But of course, we want to play with this. We want to have some different tools, buttons, or to be able to play and interact in different ways with such processes. To do so, this is why we are working in this, what we call extraction laser light. And what are the different properties that we are structuring? So we can structure the intensity of these properties, the phase, the intensity of these beams, the phase of these beams, and the polarization of these beams, basically. And we can play not only with an homogeneous intensity, phase, and polarization, but with a non-homogeneous, which means with different intensity distributions, phase distributions, and polarization distributions. So, and we've identified, and many people have identified that having these shaped laser beams in such timescales, we can have applications in many different fields, like in spintronics. I will talk about this later on, and also with magnetic storage, for nanometrology, these shaped beams, to study chiral nanostructures, or to, for example, to study ultrafast dynamics of inertial processes. Okay. So in Salamanca, during the last years, we've been working in adding these gadgets, this structuring these laser pulses. Yeah, we've been, for example, we've been able to generate attosecond vortices, to play with the polarization of these pulses, to create. I'll talk later about these Selftorque beams. Very recently, also necklace-driven beams, whatever. So in this talk, I will try to review some of these works, and at least give you the idea that nowadays we can play with this structure light. That we believe that is really interesting because it gives us new access to interact with matter in different ways. Okay. Okay. So very briefly, in Salamanca, we are expressing in the theory of this. Okay, we are expressing simulating high harmonic generation. Okay, to predict actually what we've done several times already is to predict what are the conditions that we need to generate this kind of pulses, but also to understand what happens. So what is needed to do the simulation of harmonic generation? Basically, the such resolution is to solve the time-dependent Schrödinger equation in each one of the atoms that we have in our target. Okay, this is Hamiltonian. We get the electric field here. Okay, and basically is to solve what you can see over here. This is the evolution of the electronic wave packet. But you see that we have a linearly polarized electric field in this direction, and the wave packet is oscillating. Yeah, it's being ionized and driven back, etc. And during these recollisions is where these higher order harmonics are being emitted. One of the problems we have is that in a gas jet, we don't have just one atom. We have like a trillion atoms. So we have to solve this not just one time, but many times. So this is one of the problems that what we have and we need to solve. And we have one of the problems. This is really a computational challenge to make these simulations, because first we have very different space scales. We have to resolve our simulations from nanometers to have properly the quantum dynamics at such dimensions in each atom, to centimeters to where we have these gas jets or gas cells in which we have all these atoms. But also in the time scale, we have to resolve different timescales from few femtoseconds, okay, to have this dynamics well resolved, and also to several femtoseconds, which is the duration of the driving pulse. So you can see there are many orders of magnitude, especially and temporally involved in the simulation. It's not straightforward, but so what we've done is to make some approaches to facilitate our life, and to make that we can perform, we can make the simulations in supercomputers. So we've done some approaches for the generation part. Okay, we use what we call the extended strong field approximation, and also for the propagation. Okay, we consider what we call the ferromagnetic propagator in discretized target. I will not enter into the details. I just wanted to give you a brief idea of the challenges that we have to face to solve this. Okay, so now that hopefully I give you already a glance of where we are, where we have this, how can we generate these attosecond pulses? Let's go to a structure. This attosecond pulses. I'm going to structure. I will be talking about the angular momentum of light. So I will be talking basically about 3 different families of beams that we are going to generate, which are the vortex beams, vector beams, and vector-vortex beams. And let's see what I mean by these beams, what are the main properties, and how can we generate them through harmonic generation. So when we talk about the angular momentum of light, we have to distinguish between 2 very different kinds of angular momentum. We have the spin angular momentum, which is related to the polarization. And spin, we can only take 2 values, -1 or 1, which is basically left circularly polarized or right circularly polarized. If we have combinations of photons which are left and right, you can end up with an average of spin 0, which is linear polarization. And this happens at the microscopic scale. I'm talking to this because when we talk about orbital angular momentum, we are going into the macroscopic scale. We are talking about the whole beam. And the orbital angular momentum stands for the phase distribution of the whole beam in its transverse profile. We are plotting the phase and the intensity of different beams with different orbital angular momentum. No orbital angular momentum is a standard Gaussian beam that we all know. When the phase profile of this position is flat, and the intensity profile is a standard Gaussian. When we add orbital angular momentum, which is characterized by the topological charge, this quantity here, we have this phase variation along the transverse profile. In this case, the phase is varying from 0 to 2 pi, which is just 1 jump from 0 to 2 pi. This is OAM, or topological charge of 1. If we have 2 phase jumps from 0 to 2 pi, L equal to 2, and so on and so on. Okay. The good thing when comparing spin and orbital angular momentum is that the spin is restricted to -1 or 1. Orbital angular momentum is not restricted. It's from -infinite to +infinite, but of course with discretized values. And if you can see here, probably you've understood already that the intensity profile of these beams is like a ring or a donut profile because we have a singularity of phase in the center over there. Okay. How these beams propagate? So they propagate this helical waveform. We just look into a phase and we follow this phase. We are then looking into the waveform. You have these helical waveforms that we have into these beams that can be very beautiful if you go to higher order. Okay, and how can we relate the 2 properties? And I like to do this for those of you that still have not fully understood it. We can relate it, for example, by plotting the polarization in each one of the points. In this case, these beams are linearly polarized, which means that at every point in this beam, the laser light is linearly polarized. You can see the green arrows over there, which in this case are out of phase because, of course, the phase is different at each position in one of these cases. But these beams, of course, can exhibit every kind of polarization, from linear to elliptical to circular, whatever. Okay, this is how can we more or less relate these 2 properties. Okay, and this, can you now imagine where this journal is talking about this donut shaped light? Well, this is the why it was called. Okay, we have the donut now. So what is more or less the history of the orbital angular momentum of light? Because it's a property that is emerging nowadays. It was not very well known. Nowadays, the applications of these vortex beams, I didn't tell you, but well, these beams are also called as vortex beams because the vorticity they exhibit at the center. It started in 1992 with this paper by Allen, when they associated the helical wavefront of a beam with the orbital angular momentum. Okay, it was the birth over there. From there, there have been already many applications, as you can see over here, optical tweezers. Okay, so optical tweezers actually was recognized by García in 2018 too in the Nobel Prize. beams with orbital angular momentum can be used, optical tweezers, for quantum optics, for optical communications. Here I give you an example, 2016, where there was a communication from La Palma to Tenerife, where the communication was purely through the OEM of the laser light. Okay, so all the information was encoded in the orbital angular momentum of the beam. And you can imagine, as I told you, there is an infinite number of values of OEM that you can put into your laser beam. This is another way to encode information to your beam. They are used also for imaging and microscopy. And during the last years, since 2012, this was the first work of Highorder harmonics with the OEM, in which let's say that there were new capabilities of OEM translated into the high frequency domain and also to the attosecond regime, which is what I'm going to talk about today. Okay, with the prospects, the main prospect I like is that we can transfer, we can think, and this is difficult, but we should think about it. But someday we could do this, to transfer OEM to atoms, or even to explore OEM-driven electronic transmissions. Okay, so now I told you what are these beams with spin and orbital angular momentum. How can we generate them? So to generate a beam with a spin angular momentum, I think we all know from basic optics, we just use a quarter wavelet. Okay, and we can convert with a quarter wavelet a beam which is linearly polarized into circularly polarized. Okay, most of us we've done this at some point in our life. But how can we imprint orbital angular momentum? So to imprint orbital angular momentum, we can use what is called, for example, a spiral faceplate. Okay, which is a faceplate. The thickness of the plate is different for each azimuthal position, and we can imprint very easily orbital angular momentum. The problem is that these techniques are very efficient in the visible or in the infrared regime, okay? Because we can use optics. If we go to the higher frequency regime, most of the materials are transparent to these frequencies, and we cannot use them. So here is it was the project of how can we translate all these properties into this high frequency regime that is needed to generate attosecond pulses. And the answer was in harmonic generation. This is at least our answer, in which the paradigm is different. Is instead of imprinting angular momentum into a laser beam, why don't we just generate the laser beam directly with these angular momentum properties? Okay, so the idea is, okay, if we drive harmonics with an infrared laser pulse which already exhibit spin and orbital angular momentum properties, how are these properties translated into the harmonic pulses, into attosecond? Okay, so this is what is going to be about the rest of the talk. I will tell you how can we translate these properties, because, well, it's not trivial. If it was trivial, then I will not be giving this talk here. But it's not trivial, but it's really beautiful the way it's translated and how this is really happening. Okay, if we start with the spin angular momentum, we can face the problem. The first problem up to now, but everything I've told you up to now about harmonic generation was considered linearly polarized. Okay, actually, if you remember that movie with the electronic wave packet, the electronic wave packet was moving along the direction of the linearly polarized electric field. The problem is we drive harmonics with a circularly polarized driving field. The electrons that are ionized then are driven away from the parent atom, and they don't recombine back. They never recombine with the parent atom again, as you can see over here. So we end up with no harmonics. So for a long time, since the harmonic generation, it was the first experiments were done in the late 80s. It was not until 2012, 2013, where the first experiments of harmonics with polarization different from the linear were obtained. Okay, actually, you can see here these experiments in 1994, where it was clearly shown that when the elasticity of the driving field was already 0.2, the efficiency of the harmonics was really, really low. So I will not enter into detail into how this was solved. The idea is to somehow to manage to change the driving field, to play with different configurations of the driving field to be able to generate harmonics. Nowadays, there are many techniques, as I can show you here, but I will tell you one of these, which is really beautiful. This one, the idea is quite easy. Is okay. I've told you that if we use a circularly polarized driving field, electrons are ejected away from the parent atom. Yeah. For example, if we are using right circularly polarized, but if we use another beam, which instead of just right circular is left circular, you can maybe drive the atoms back to the ion. The problem is that if we have right circular plus left circular, this is linear polarized. So we are exactly at the starting point. But the idea here is to use these two beams, but with different frequencies. Okay. For example, omega 800 nanometers, which is right circular, and 2 omega 400 nanometers for the left circular. And in just such case, which is it's not easy to imagine, okay, to figure out how is this electric field, which is that field over there, this 3-point field. In that case, we have recollision and we have harmonics which are circularly polarized. Okay, this is one of the ideas. Okay, but there are, as I told you, there are other schemes by playing with the driving field. So, but let me start talking about vortex beams, which is translating orbital angular momentum into the Highorder harmonics and then into the attosecond pulse. So the idea is again is how a vortex beam is translated from the infrared to the extreme ultraviolet through harmonic generation. So we can start, for example, with a vortex beam of topological charge equal 1, this is the intensity and phase profile, and how are the harmonics emitted? So this was not easy to understand, and I will tell you why. But if we perform the simulation, what we saw, sorry, is that every harmonic order, 13, 15, 17, 19, 21st, were generating with a topological charge that was proportional to the harmonic order. This was the scaling of observed. Okay, and this, I think, it can be understood quite easily looking into the photon picture. If we go into the photon picture, we can understand that we have photons with L equal 1, and we are absorbing, for example, for the harmonic 17, we are absorbing 17 photons with L equal 1. If we impose conservation of orbital angular momentum, the photon that is being emitted needs to have L equal 17. Okay, so it can be more or less understood. I told you that it was not easy because there was a first experiment. Oh well, yeah. There was a first experiment that was called in 2012, in which this was not observed. It was observed that the topological charge of harmonics was exactly the same of that of the driver. It was very controversial. Fortunately, there's been more confirmation, experimental confirmation afterwards that confirmed that conservation laws in physics work. Okay, so how are the spatial and phase profiles of these harmonics? These are results from our simulations. You can see, for example, two harmonics here, 17 and 23rd. This is the intensity profile, atomic profile. Okay. If we look into the phase profile, you can see that in this case there are 17 phase jumps, and in this case 23 phase jumps along the transverse profile. But of course, you can start counting, and you have to believe me. But instead of believe me, what we can do is to do a trick or be a little bit clever and to do the azimuthal Fourier transform. Do the Fourier transform along the azimuthal coordinate, and we do that. We obtain over here. You can see that here we have 17, and in this case we have 23. It's much more easy than counting phase jumps over there. Okay. One result that has been just accepted is impressive. Is this one? Is this we've been collaborating with the in the University of Paris-Saclay, and they were able to measure experimentally orbital angular momentum of the harmonics up to 100. Okay, by driving the harmonics with L equal 4, the 25th harmonic following this law, we have an OAM of 100. You can see that this is the experimental measurement of the topological chart. It's quite noisy, but it's not that noisy because what they measure is the wavefront of the beam, which is the result over here. And the waveform is smooth, and it has more or less this value of 100. The problem is that if we do the azimuthal Fourier transform. The azimuthal Fourier transform requires cylindrical symmetry. As you can see that the bin is not fully symmetric experimentally. That's why this noise appears over here. But we are quite confident that we are having this OAM over there. So as I told you, within OAM, the good news is that we can have many values of OAM over there. And with harmonic generation, in principle, we could go to very high values. Okay. So the next idea, and this was quite simple, after the first work we did, 2013, then we ask ourselves, okay, what happens if you drive harmonic generation instead of just one beam of orbital momentum with two beams with different orbital momentum? So for example, we have here with L equal 1 and L equal 2. And what happens now is that each harmonic, instead of having one value of orbital momentum, we have several of them. Why is this happening? Again, we can go to the photon picture, and we can think now that we have like two bags of photons with L equal 1 and L equal 2. And to create the 17th harmonic, we have different pathways, different ways to, depending on the number of photons we take from each one of the bags. Okay, and depending on the number of photons, of course, the orbital angular momentum of each channel will be different. Okay, so that's why every harmonic order has many values of OAM. How can we control which is the value that is more prominent? Just through the intensity ratio between the two drivers. By changing the intensity ratio of the two drivers, we can control which of these channels is the is dominant. And this is important from what I'm going to tell you afterwards. Sorry. So this is the intensity profile of the 17th harmonic. This is the phase profile. Now it's more difficult to count here phase jumps, actually it's impossible. Yeah. But if we perform the azimuthal Fourier transform, you can see this broad distribution of orbital angular momentum for this harmonic. Okay, so what we were thinking after was, okay, how can we move this distribution by changing the intensity ratio? So what we were thinking afterwards is what happens now if we delay the two beams. Okay, we have the two pulses and we delay them in time. As you can see over there, what happens is that you end up with a laser pulse in which, at the front part of the pulse, you have L equal 1, at the rear part you have L equal 2, and in the middle you have a combination of L equal 1 and L equal 2 with different weights. Which means, from what I told you in the previous slide, is that you will have an OAM distribution that will be changing in time. Okay, you can see here in this movie. In this movie, this is the phase profile of the 11th harmonic. This is the intensity profile. This is the OAM. We are now at this starting position from L equal 1 for the 11th harmonic. We have L equal 11. But if we start going in time, you can see how the OAM is changing from 11 to 21. It's changing smoothly depending on the weight between these two parts. The good news here, it was, okay, we are, for the first time, we are generating a laser pulse in which the OAM is changing in time. This was not done before. And this is more or less the result. With these two combined pulses, we end up with this pulse in which the orbital angular momentum changes smoothly in time. And this is the Selftorque of light. Okay, in analogous with mechanics, variation in time of orbital angular momentum, this is what is the torque. Okay, and this is why we denoted these pulses as pulses with here it was quite sounded. And also the good news it was that our colleagues at Colorado, they were able to generate this and measure this experimentally. Actually, well, this is the experimental and theory profile of the beam, and you can understand now why this croissant shape like is, because these pulses, they exhibit this croissant shape over there. So how can we measure this experimentally? Just to give you a very brief idea, it seems really complicated to measure such a smooth variation in the attosecond timescale or sub-femtosecond timescale of OAM. It seems really complicated, but it's much easier than expected. This is just a little bit. I will not go into detail. For those who know what is the chirp of laser light, the self-torque is related intrinsically with an azimuthal chirp, okay, which means that along the azimuthal coordinate of your laser beam, there is a chirp, there is a change in frequency, okay, that is unequivocally related with the torque. So in the experiment, just by measuring the frequency content of different parts of the beam, they were able to confirm that this torque was there. And here is the very nice agreement for different harmonic orders between the theory and the experimental results. Okay, I'm a little bit late. I'm going to faster here. So this was for the first part of the vortex beams, but now we have also this very interesting vector beams. What's the difference between a vector beam and a vortex beam? A vector beam is no more than a beam in which the polarization is changing spatially. Okay, we have a certain distribution of polarization. For example, in this case, we have a radially polarized vector beam. The good news is that we can understand these beams as a combination of beams with orbital angular momentum. Actually, this beam is no more than the combination of a left circularly polarized beam with L equal -1 and a right circularly polarized beam of L equal 1. And this will help us a lot when understanding the conservation laws and the physics of this beam. Okay, just to give you an idea of what are vector beams used for in the femtosecond regime or in the infrared regime. One of the properties of radially polarized beams is that if you focus them tightly, it's a longitudinal component that appears at the center, okay, that has very good properties for imaging because actually the size, the spatial size is reduced from standard non-vector beams, from standard Gaussian beams. Okay, so here's an example of a collaboration I did recently with Juan Bueno in Murcia, where they were imaging with second harmonic micromicroscopic images. They were imaging collagen fibers in cornea. They measured, they were able to see that with vector beams, the resolution and the efficiency of those images was much better than the standard. That will give you a brief idea. I will give you later on a brief idea of azimuthally polarized. Okay, so we go back to harmonic generation and let's try to translate these beams into the frequency domain and the attosecond domain. Life seems easier here because if we derive in a gadget, we derive harmonics with an infrared vector beam, and each point we have linear polarization. It means that this polarization distribution will be translated directly into the higher frequency regime. Okay, and this can be understood again from the orbital angular momentum content, because we think that this beam, as I told you just in the previous slide, is composed of L equal -1 left plus L equal 1 right. Okay, and now we apply orbital angular momentum conservation. Again, we have two bags of photons. Okay, one with L equal -1 and another with L equal 1. So we can start. We have many channels, yeah, depending on the number of photons we take from each one of the bags. But now there is a restriction because we cannot have more than one photon from one bag with respect with the other. Why? Because the total spin angular momentum cannot be 2 or -2 or higher. It can only be 1 and -1. Yeah. So due to the spin angular momentum restriction, we can only have two channels in each one of them. And actually, the only two channels that are allowed are -1 and 1 for each one of the harmonics. So we have the vector beams with very similar features as those of the infrared driving beam. So this we did the experiment in Salamanca with Iñigo Sola, and we were able to measure and to characterize vector beams in higher harmonic generation. I will not go into the details. And one thing that we are working very recently is that changing this is an emerging field in harmonic generation, which is instead of working with gas jets, working with solids. Okay, why don't we drive harmonic generation in solids? Okay, there are different goals with this. because well, people at the first they believe, okay, in a solid we have more atoms than in a gas jet, so the efficiency will be higher. Okay, but in a solid, of course, it's the dynamics of the electrons are more involved. You have to take into account the band structure and all many things. I will not go into detail. For what I'm going to talk here, there's something very interesting for us, is that a solid can be anisotropic, and with respect with a gas, which is isotropic, which means that the response of the material will depend on the polarization direction of our beam. Okay, so for example, here I'm showing you simulation results of harmonic generation in graphene, okay, in a graphene layer. So what I'm showing here, this angle here is the direction of the linear polarization with respect to the graphene layer. And depending on the direction on this angle over here, theta, of the laser beam with the graphene layer, the harmonics are emitted with different polarization, as you can see over there, which is when this medium is not isotropic. Okay? And this is very well reflected when we are driving harmonics with a vector. If we drive harmonics with a vector beam, what we end up having here is that you see that the shape of intensity shape is not anymore that one that we have the donut profile. It's more involved, and it has a lot of information of the dynamics of the electronic dynamics that are happening in the graphene layer. Yeah? And actually, we go and look into the orbital angular momentum content. What we see that now is the orbital angular momentum content of this harmonics is not that as easy as it was in this case. Yeah, this is because due to the anisotropic nature of the graphene layer, there is a spin orbit coupling, yeah, in harmonic generation. Okay, so for example, in these cases, you can see that apart from -1 and 1 from the driving field, we have contributions of +6 and -6 OAM. This 6 number is related with the symmetry of the graphene of graphene. Yeah. Okay, these are very, very interesting results that we are working now. Okay, so to end up, one of the things we've been working also is to combine vector and vortex beams. Okay, which is that we have a vector beam and we add OAM to a vector. It can be decomposed again into beams. Yeah, now with L equal, in this case, with L equal to 1 and 3. And well, I will not go into the detail. This is a collaboration with Paris-Saclay. And the propagation dynamics of a vector vortex beams are more evolved and not as easy because those beams are not stable upon propagation. The properties, they change upon propagation. So what we were able to see, I tell you, is the properties of the harmonics that are emitted. And in this case, different from what happened in standard OAM beams or standard vector beams, what is conserved is what is called the pan-Karatinam topological chart. Sorry for the pronunciation, which is a topological chart that takes into account both orbital angular momentum and the polarization distribution. Okay? And that is the chart that is being conserved, not the standard OAM. Okay, so I promise I will tell you another application of vector beams, and one of the interesting applications for us for azimuthally polarized vector beams is that these azimuthally polarized vector beams, they exhibit a magnetic field at the singularity of the electric field, yeah, longitudinal magnetic field. And this is very interesting because with these beams, they are generated, as in this case, in the femtosecond timescale, that we know how to generate them now. We can obtain very intense magnetic fields at the femtosecond timescales, or even thinking about attosecond timescales too, which are very intense, which are in the amplitudes of Tesla. Okay, and this is we are working there now quite a lot. For example, we've been working now in what happens is we have harmonic generation, but we add a magnetic field. Okay, of course, in harmonic generation, the driving field, it has the electric field and the magnetic field already. Okay, it's an electromagnetic field, but that magnetic field is very weak. Okay, compared to the electric field. That's why up to now I have not talked about the magnetic field at all. But what happens if now we add external magnetic field which is intense enough to do something with the electrons there. Yeah, and we know that we can generate those magnetic fields there. So we've seen, for example, that the harmonic efficiency can be increased, or even we can extend the harmonic orders, the cutoff towards higher frequencies. That is something we are working on. So, another thing that we are also starting to work is in ultrafast magnetism. The timescales in magnetism more or less are summarized here, and there is a gap when you reach the femtosecond, attosecond timescale. Okay, we don't know how are the magnetization dynamics at those timescales, and we believe that now we have the tools for the first time to explore magnetization dynamics, for example, in such timescales. Okay, so for example, that is going to work. This is a simulation that was done in our group, which is, for example, to play with magnetic textures when shining ferromagnetic material with this kind of laser colors that you can see over there. Okay, we can play and try to generate new magnetic textures with this kind of things. Okay, so I hope I convinced you that now we have a lot of tools to play with his timescales of attosecond timescale. What fascinates me is that looking at this graph is that we may know what's in this direction. Yet it's very difficult to think something that is larger than 10 to the 18 at the edge of the universe. What's there? We don't know that. But why don't we think what could happen even with shorter pulses? There are proposals already to generate septosecond pulses, which is 10 to the -1. So I think there's a lot of room there for doing very interesting things. Let me thank the people in our group in Salamanca. It's a very bright people. We have theory, we have experiment. I'm really happy with the group of really nice people we have there. And let me highlight the people that is working in this part of theory of harmonic generation and science. Of course, of the work by our students. Most of the work that I present here is done by them. Laura, which was a former student, now she moved to Imperial. Roberto, Ana, Alba, Rodrigo, and Victor. And also a lot of credit goes to Luis Plaza and Julio San Roman. So also let me thank all the collaborators that are involved in the work I've presented, mainly the people in the group of Henry Captain and Marco Hernández, the group of Nick and Chen in Gua, and the group of Sophie Casanes in Paris-Saclay and Selftorque in Mans. And that's all. Thanks a lot for your attention. And if you have any questions or anything you may be interested, please don't hesitate to contact me.
Thank you, Carlos, for the interesting talk and also for the nice introduction you did so that we can get information about what you are talking about. Now we have time for questions. Also, people watching the seminar in YouTube, if you have questions, please write them in the chat. Questions here or comments? Rebecca, maybe you can repeat the question because I imagine that okay, well, I have a question. That's fine. No, you are talking about it. Okay, are you asking English or? Okay.
As you want.
Okay, I don't get it. Pero en la sala no tengo que dar en inglés. As if, not as if you didn't have near field on parties, no? Like in the normal you do drift to your party, and then most of the physics that you were interested in happen in the near field, the focus, and then that's the Fourier transform. What happens with the state? Or is it?
Those are Laguerre-Gauss modes. They are stable upon propagation. So the Laguerre modes of L = 1 or L = 2, or even combination of those modes, they are stable upon propagation. So what I've shown you, the far field, is very similar to what happens in the near field. The only thing that may change, and this is true is that the divergence of different modes is different. Okay, L equal 1 diverge. The divergence is lower than L equal 10, for example. So if you have combinations of OAM modes which are quite different, then you have to care about it. But for combination of L equal 1 and 2, as I showed you, or pure modes, they are stable. So what happens in the near field? Directly, which is not happening in the vector-vortex. In the vector-vortex is a mess. It's completely different. So you have to be really careful what is happening from the near field to the far field. Actually, yeah, when this experiment, we were really thinking what is happening in the near field, and then translate it into the far field to have a vector vortex in the far field. So the structure in the near field was different. Yeah. Oh, I didn't repeat the question. Well, the question was if this is what a stable propagation or what happens from the near field to the far field. I think.
If you have another question, you can ask. That is your isotropy, no? Have you considered molecules, laser line molecules that have the benefit of phase?
Totally, it will happen very similar. We have not considered them because we are not working with molecules, but yeah, very similar thing. It's a possibility. Yeah, totally. Actually, one of the sorry, again, the question was if considering molecules instead of solids for having this anisotropic nature, generating these beams. One of the solutions to generate circularly polarized light, instead of playing with the driving field, as I said, is playing with the target too. If you change from gas targets to a molecular target, you can have recombination. You can have emission from one and going to the other, but you cannot have circularly polarized. Circularly polarized molecules, it's not possible, but elliptically or high elliptically, yes. Yeah.
I also to ask you something. Regarding the experiments in Salamanca, you are doing the vector beams or only that? Only. I mean, but what I mean is that what energy do you have in these pulses? I mean, it would be possible, for instance, thinking about using these pulses for processing, or the energy is too low for that?
So the intensities we need to reach there and then to the 14 watts per centimeter square. The intensities you have for processing are lower than that. Yeah, this is what I think. In Salamanca, we did the vector vortex. Actually, we don't do them in our university in the facility. We did them in the CLPU, Centro de Láseres Pulsados, where they had the system. Actually, the gas jet, the vacuum chamber, and the spectrometer, where we can generate and measure the harmonics. So Inigo and me, we went there for 1 week, and we were able to experiment to observe this vector.
More questions? Okay. We have no more questions for the presentation, and also we have more present for you.
Thank you.
Okay. Thank you, Carlos.
Thank you.